Hello, my name is Livingston and I'm in the chemical engineering department. So for my research that I am working on right now, I am modeling and designing low-cost optical particle counters. In short, I'll be calling them OPCs. So I'll just talk a little bit about what these instruments are. So OPCs, they are sensors or instruments that are used to measure particulate matter in air. And they come in various forms and various makeups and various prices. So as you can see, some really cost that high and some are very low. My focus is on the low cost ones because they are the ones that really come with issues because people try to reduce the prices. They also compromise the quality of what they are doing. Now, these instruments, if they are really designed well, they're able to give very good results as in measuring the concentration of particulate matter that are in the atmosphere at a given time. So this is what I'm going to talk about, and that is what I'm actually working on. So this is how these instruments work. So it's on light scattering and light absorbing principle. So it has a laser and the particle goes through the geometry or the region within the design of this sensor. So as the particle is going through it, the laser intersects with the particle and then it gets scattered in various angles. So there's a detector that detects the light that is being scattered. And not all of them, but most of them have mirrors or lenses. So focusing mirrors or lenses to focus this scattered light onto the detector. And the detector measures the intensity of this scattered light. And there are some algorithms that are written for it to calculate the concentration of the particles. So this is how these instruments, they work. So with what I am doing right now, eventually I will model like one commercial one, like these commercial ones, I'll model one of them. But for now, these are some random geometries that represent the OPC that are in the market, which are being sold. And most of them, they go through some tortuous path. The path is not straight. They go through some ways before they get to where the detector is. So they have a lot of issues. And that is why I'm modeling these things to access the efficiencies of these instruments. So this is one geometry, random geometry that I built just to verify how these instruments, they work. So after using the CAD, I use CAD SolidWorks to build that geometry. I import it to the CFD, Computational Fluid Dynamics software that I use. It is called Converge. And that is what I use to build the case setup. So I define the injector that I want to use. And another important things that I also consider are the boundary conditions, the flows and the pressures at the inlet and then the outlet, and also the wall. We specify whichever conditions that we want to put over there. So to my right hand, over here, that specifies the various parameters that I'm supposed to input in when I'm doing the case setup. Now, one of the most important things in my case setup, it is my grid or mesh generation. Because with this, I am breaking the whole geometry into smaller elements in which the governing equation that I'm going to choose for my for this to be solved to be applied on those elements. So we know that it does a lot of like computations, and those complex equations are being discretized or divided into simple algebraic equations for them to be solved. So the more mesh or the more elements that I generate in my mesh generation, then the more computational resources is also needs for it to achieve whatever that I'm looking for. That is my resolution. So if I get better or good grid generation or good mesh generation, I get better resolution. But then there is a trade-off between how do you call it, my resolution and then the computational time and resources. The more finer it is, and then the more computational resources and time that I also need. And that is something that I'm still working on to know the optimal computational resources that I need for my simulations. So I also specify which equation that I want to solve. And these simulations that I'm doing, it is turbulence modeling. And it uses the Reynolds average Navier-Stokes equations. That is what it solves. So it's a whole lot of equations that is solving. So that's why it needs more of computational resource, and we need something that will be able to solve this and give me an output. And using the computer or the laptop that I use in my office, it's not going to do anything. It might take me years for me to get an output for my simulation. And that is why there is the need for me to use a high performance computing for my simulation. So these are simple scripts that I wrote for that I use to run my simulation. So currently this is what I'm using. So you can see the wall time, 168 hours. That's a lot of hours that I'm using. It's almost like 6 to 7 days. And the processes that it's using. So I'm using OpenMP for my parallelization in the simulation that I am doing. It's been working pretty well for me with the memory that I use and the number of tasks. So because I'm using OpenMP, the node that I'm using is only one. And so this is just a simple scripts that I have for that I use to run my simulations. Unfortunately, this is taking much longer time. So as I said, I am still working on getting an optimal parameters or values that I need to specify, so I'll be able to have better resolution and then also have faster and efficient simulation time on the supercomputer. So after I do this, I download the output files, and then I send to the supercomputer for it to run. So this is an example of one of the geometries that after it runs on a supercomputer, then I download it. So this one currently, it ran for about 7 days, and the real simulation time that I got after the 7 days, like 120 seconds, which means that the performance was not very good. So I'm still looking at it. Maybe I can use an MPI instead of OpenMP, or perhaps I can combine both, or I can also throw in more processors, of course, to see if that will help. So this kind of computation, I intentionally did this, but this one had some computational errors in it. And you can see because of that, the particles that are supposed to go through it, if you can see, they are stuck. They tend to stuck on the walls. They are stacking on the walls of my geometry. And that is not what I'm expecting it to be. So in this, it means my mesh wasn't good, or the grid wasn't good. So I had to go back and go and increase the grid. And that was what is affecting my running time right now. And the very reason I am working on it. So the supercomputer is really doing a good job running my simulations for me. Now, this is a better one, a final one that I now have, which is doing a very good job. And yeah, I will leave it to run more and then see how these particles are going through my geometry and coming out of the exit. So basically, that's what I am doing for my research. I will leave this one to run for some few seconds just for you to have a look at it to see how my geometry works. Okay, so I can go on. So in conclusion, using high performance computing is very, very important, because without it, I'm not sure I'll be able to get the resources that I need for the research work that I'm doing, because my research work is computationally demanding, and having the supercomputer to run it, it's a very good one. And I'm still looking at parameters and things that I can use to optimize my script so that I'll be able to get better resolutions and better running time simulation times. Yeah, thank you.